So on March 7, I gave a talk on flipped classroom and self-graded homework at a STEM conference at Georgia Southern. This conference was organized, among others, by Joy Darley, who invited me to report on this, and I want to thank her for that, to give me this opportunity to share some rather modest findings. Modest because I'm not going to provide any theoretical framework for flipped classroom, but rather focus on the logistic aspects of a flipped classroom, and also of the use of self-graded homework, which I think might be relevant whether you flip your classroom or not. So I will focus on logistic aspects and practices that I found seem to be conducive of student learning. So where I was coming from in deciding to try to flip the classroom, I've been teaching a lot of calculus, and what I will be reporting on is specifically a second college level calculus course, second semester of calculus. But of course, a lot of the things I will discuss could be adapted to other courses. But basically, this is one of these courses, and there are many more, where you have a conceptual aspect and a technical part. And we tend to spend the time lecturing on the conceptual aspect. And for the technical part, we do a few examples, and then we hope for the best in some sense. So we have to assign a lot of homework to hope that they will learn the technical aspects. And at the end, we really test them on this technical aspect. So how do we remedy that? We have to deal with the challenge of providing a training on the more aspects of cracking calculations up. And what I've been doing over the years, in my department, we've been relying on MyMathLab. Some other places relate on other automated homework systems. I've been using it many times, and it addresses some of the problems, but I've remained somewhat frustrated with it, in part because it still focuses on the final answer. So either you pick an answer in a multiple choice fashion, or even when you enter an answer, it's focused on the final answer rather than the process. There is not the proper focus on writing, explaining the process, properly describing the steps. So I thought that maybe flipping the classroom could address some of these concerns, and I want to share with you a little bit how I think it does. So the general model here that I've been applying is that for each class, as you know, in a flipped classroom, the students are assigned a set of videos to watch, and I will say more about these videos in a moment. I've decided to also provide corresponding notes for the videos, because I have found that otherwise weak students tend to watch the videos and not take proper notes. And then when it comes time to review for a test or something like that, they don't have the time to watch all the videos over again, and they're kind of lost. So I'll go back to these notes as well. For each class, they have an homework set that is assigned, and that is on the previous material. So not on the videos that are assigned for that day, but on what we have worked on the previous time. And in class, when they come in, the first thing they do is grade their own homework, and I will come back to that as well. And then we do a quick recap on the material covered in the videos. This is a question and answer type of things. I take questions, of course, if there is any, and then we work on a worksheet on the material. The quick recap, the point of the quick recap is to make sure that everybody has at least the minimal that they need to work on the exercises of the worksheet. So let me say a few more words on the set of videos. For the purpose of a fully online course, I have developed a complete set of calculus videos. So here you have a screenshot of a YouTube playlist for Calculus 2. This is the course I'm talking about. And you see that there are 109 videos corresponding to 21 hours of lecture. Now, of course, in a regular setting, when I used to do lecture on the board, I would use maybe 40 hours a semester, maybe, I don't know, somewhere between 35 and 40 hours a semester of lecturing. All this fits in a little more than 20 hours with these videos, because it's a computerized presentation, and that allows for things to flow more easily without taking the time to write on the board. What I want to emphasize here is that in some way, by flipping the classroom, we cheat a little bit, because all this lecturing time on the concept, we dump it on students. Now, it's half of the lecture time, so it's a compromise. We dump 20 more hours of work on the students. So in some way, it's not surprising that we get better results, but it does work. I'm very happy that I could use my own videos, because then I control the content. A lot of flipped classrooms rely on a mix and match of videos found on YouTube, and then what you get is a best approximation of what you want, but never exactly what you want. And there is also the problem of consistency, that when you switch topic, you're going to often switch the source, and you get a very inconsistent type of presentation. So I didn't like that too much, and I'm happy that I could develop a full set of videos for the course. They're organized in learning modules, so that's why this M11 is the first video in module M1, and I'll get back to that organization in modules later on. Now, I'm not going to play an example of a video for you, because it would take a little too much time, but I'm still going to give you an example using material developed for these videos. So to give you an example, let's say we are looking at parametric curves, and in the previous video we established this formula on the right hand side of the screen for the length of a piece of a parametric curve. And now we are looking at what we obtain when we rotate such a piece of parametric curve about an axis, generating a surface of revolution. So you can explain that if you pick a point on the curve and you rotate it about this axis, generates this circle centered on this axis, and if you do it for every point on the curve, you generate this surface of revolution. And now we want to calculate the surface area. So what do you do? At this point in the course, we've already established a number of formulas, integral formulas, with the same principle of approximating what we want to calculate by things we know how to calculate on small pieces, building a Riemann sum, and then the limit of the Riemann sums gives us an integral formula. So here you do the same thing. You look at the interval of the parameter t, cut it in pieces, that corresponds to cutting the curve in pieces, and then you look at a particular point, look at what you generate by rotating this part of the curve about the x-axis, you get something like that, and now you want to calculate the surface area of that, and calculate here really means approximate. So how are we going to approximate the surface area of something like that, assuming that the piece of curve from the point of parameter tk to the point of parameter tk plus 1 is relatively small? Well, we're going to approximate it by something we know how to calculate. The first observation is that this length here, we have a formula that we've established before that we can use to calculate this length, and we want to approximate the surface area of the red thing. So we are going to pick a sample point tk star in the interval from tk to tk plus 1 that corresponds to a point on the curve, and when we rotate it about the x-axis, that generates a circle, and this circle is of course drawn on our red piece of surface, and we approximate the red piece of surface by a circular cylinder. Its height is, well, the length of the piece of curve that we're considering. And the other thing we need is the radius, but the radius is given by the radius of the circle that we just drawn, and you see that this radius is given by the value of y at the point of parameter tk star. So now we have the dimensions we need for the cylinder. How do we get the surface area of a cylinder? Well, we can again use the power of computer animation to illustrate this and show that if you have a cylinder, you can open it and you get a rectangle. And then it's easy to see that when you open it, you have one side that corresponds to the circumference of the circular base of your cylinder, and the other one is the height. Okay, and then you go from there to write out your Riemann sum and eventually the integral formula you're seeking. I'm going to turn to a second example very quickly that I didn't touch upon in my presentation on March 7 at the conference because I had more of a time restriction. Here I can go on and on if I feel like it. But I don't really feel like it, so I'm just going to go with one simple more example from Calculus 1 rather than Calculus 2 on the mean value theorem. So the mean value theorem, under the proper assumption, you have that the value of that the derivative takes a value that corresponds to the average rate of change of the function over the interval. And of course, when we present the mean value theorem, we point out that the theorem of Hull that we've presented before is a particular case, right? The case where the function has the same value at the endpoint, then we get that the derivative takes a value 0. In other words, you have an horizontal tangent. Now graphically, the mean value theorem, the interpretation is something like that. We have a smooth function, continuous differentiable function going from af of a to bf of b, and this number is the slope of the secant line that joins the points af of a and bf of b. And of course, f prime of c is the slope of the tangent line at the point x equals c, corresponding to x equals c, and therefore what we are really saying with the mean value theorem is that there are tangents that are parallel to the secant line. And to prove this, even though the theorem of Hull is a particular case, we use the theorem of Hull to prove the mean value theorem. So we use the particular case to prove the general case. So that's not really surprising if you think of the fact that they are really exactly the same theorem, the theorem of Hull and the mean value theorem. The only thing we do is turn the picture around. This is a comment that we can do in class, waving n on the board, but we cannot really do it for real. And in this case, with these computerized animations, we can do it for real. Because you see that if you forget about the system of coordinates, this picture is really the same as the picture for the theorem of Hull. Right? You have the same value at the endpoints and you have horizontal tangent. And then you just bring it back here and you see that this is really the same thing. Well, to get a proper proof, there's still something to do, but I think this gives a good intuition to students on how these two results are really related. Now coming back to the flipped classroom model, I said that I provide corresponding notes to the videos. So I have actually books. Here you see that on the YouTube playlist you have a link to companion books. So there are 3 books, one for Calculus 1 and 2 for Calculus 2, and I will just mention things about the Calculus 2 books because this is the course we're talking about here. Here there is one that really gives you essentially the transcripts of the videos, where it gathers all the definitions, basic results with no proof, and all the worked examples where the full details are to be found in the videos, but you have notes corresponding to the videos, and on the other hand you have the exercise book that gathers worksheets, homework solutions, sample test with solutions, and I'll go back to all this as well. So just to show you what it looks like with an example, for each section you have direct links to the videos, short abstract, and then the basic results and definitions. Here of course it's a cropped screenshot, so there's not a lot on it, but so you have the basic results, and you also have worked examples in some details, but for the step-by-step explanations you have to go back to the videos. Now, for each class, they have a homework set that is assigned on the previous material. And that corresponds to the material worked on the worksheet the previous class period. And this homework is self-graded. So let's look at what it looks like. On the left side of the screen you have an example of a worksheet, and on the right side an homework set that corresponds to that worksheet. And you see that these are very similar type of examples. So the homework set are really doing more of the same of what we've done together in class with full explanations. And when they come in class, they pick up the solution. These are full solutions for the homework, and they grade it themselves. They don't grade the paper of somebody else, they grade their own. And so you see that at the end they put their name and their grade, and they return that to me together with their work, so that I can check if what they did was reasonable, and I can record the grades and so on. So that means that there needs to be some level of explanations on how to assign points for each question, and depending on what it is, this might be a very simple thing like here, 2 for the integral, 1 for the limit, or 2 for each part, or in some cases it might be a little bit more intricate, the explanation on the grading key. So sometimes I have margin notes and these type of things. At any rate, they grade it themselves, and so you can say, well, how do you control that they do that reasonably? Well, it turns out that really they tend to be quite tough on themselves. At the beginning of the semester, I review that relatively carefully, make some comments before I return it to them, to guide them a little bit on what is a legitimate or not legitimate way to assign the points and so on. After that, after a couple of weeks, they really get it, and they're actually quite tough on themselves, and it works pretty well, in my opinion. And it has many advantages. One of them is that it's not just entering final answers of something that they do on scratch paper. They have to write full solution, and they read the full solution that I provide them, which means that they compare what they do with what I expect in terms of explanation and presentation and so on. And I have really seen quite drastic improvement in the way they write on their test since I use this self-graded homework technique. Another advantage, I think, is to clarify expectations in terms of how much explanation I want, how I want them to present their work, and the type of exercises they may have on the test. Now all this is gathered in one of these online learning systems. The one we use is Desire to Learn. It's called Folio for the in-house version. And as I said at the very beginning, all of the videos are organized in thematic modules. And so for instance here we have Module 4, Review of Integration and Integration by Parts. Each module is organized this way with an introduction. It gives a little bit of motivation for what we're going to consider. Then learning expectations, that spells out explicitly the learning outcomes and provides a study guide for the module. So everything, all the definition of concepts and basic results that they're supposed to know at the end of this module. Then you have direct links to the videos, and every time we have the sufficient amount of lecture material for a worksheet and homework, we have the worksheet, the corresponding homework set, and the homework set solutions, which of course is made available to students only after they've returned it. And then you have several iterations of that per module. All of that has to be organized in a specific way, and the what is due on every day has to be made very clear. So here in the course orientation you have a schedule in particular, where you see that you have what are the videos to watch and the workbook sections corresponding to it for each date. Here there is no dates because it's a generic schedule by weeks. So for instance, for a particular day you may assign videos 8 to 10, indicate approximately how long it's going to take, the corresponding sections in the workbook, the homework due, which as we have explained corresponds to the worksheet we've worked on the previous time. And so it's organized this way every day until comes times for a test. And before the test, well, since we freed up some time by dumping all the lecture time on the students, we have time for a trial run, a mock test. So I usually the week before give a mock test, and what that means is that they come and take the test as if it was for real, and I give them a test that is pretty close to what I expect to give them as a test, and that clarifies also expectations in terms of type of questions and so on. And so they take it in the conditions of the test, and when they finish, instead of returning that test, they actually pick up the solution. So I type full solutions, and then they can at home compare what they did with what was expected, see what they knew how to do, see what they need to review. And again, I think this has helped tremendously. Now what about the results? The first thing I want to point out is that students tend to like it. So this is from last semester student evaluation comments. And so overall the feedback was very positive. The weak students, I think, like that you can replay the videos. In class sometimes when you explain something, they get lost, they get stuck on a detail, and then they don't follow the rest of the explanation, and they miss something important. In this case, they can go back and make sure that they don't miss anything important. One of my favorite comments here is the penultimate, of course, not only because it says that I'm laid back, but because it says the course forced you to do the homework and learn the material, and that's exactly what I was aiming at. So I'm happy that the students feel that way as well. But that's just perception. What about actual results on test? Let me point out first this blue column, which is going to serve as a control group. So what is that? I've been teaching Calculus 2 very regularly over the years, and here I have an aggregate of 8 sections that I have taught in a traditional way, assigning homework in MyMathLab from spring of 2005 to the fall of 2013. So I have looked at the average on each test for each one of these 8 sections and made an average. Now I give, I have consistently given tests on the same amount of material at approximately the same times, and I grade in a fairly consistent way, well, because these were all my own sections, so I am grading that particular way. In the fall of 2013, I wanted to conduct an experiment about this flipped classroom. I had 2 sections of Calculus 2. I decided to teach one in the traditional way with MyMathLab for the homework, and the other one with a flipped classroom and self-graded homework. And I was hoping to use this section that I teach in the traditional way as a control group, but unfortunately I had at the very beginning some pretest to try to have a baseline, and the pretest showed that unfortunately this control group was significantly weaker than the other one, and that was confirmed by the results. You see that this section also did quite worse than the average over the years. So, but the important part here is that the flipped classroom did better than the average over the year. Not only did better than this relatively weak section, but better than the average of the 8 sections in every single test and on the final. Now I like that, and therefore I continue to teach in that manner, and so this semester I have another flipped Calculus 2 course this semester, and I only have graded 2 tests so far, but you see that for the first test it was essentially the best first test I've ever had in this course, and for the second test it's more in line with what I obtained last semester with my flipped classroom, but you see that it is still significantly better than the average over 8 sections. So I think here there's pretty strong evidence that the students do learn more. However, of course, as I pointed out before, I am conscious that there is a little bit of cheating in taking the lecture time and setting it aside. We are essentially creating more classroom time. And the cherry on the cake is that you get some worldwide reach with these videos that are public. They've been watched by people in 152 countries. The books have been downloaded at a rate that surprised me, really. There's about 10,000 book downloads per month. And I've got some feedback emails from people in countries where they don't have money to buy books and this type of things, who were very happy to have these resources made available to them. So I think there is really an interesting aspect here as well. And at this point you're probably bored already listening to me, so I will leave it at that.